what is the first, like, sorry, I don't know. What is full form of CRG?
CRG was the related to planar graphs.
Acha. Okay. Crossing. You're talking about
Yeah.
crossing number.
Right, right. Yes.
Okay. So we'll check that. Yeah. You can check that. So did Santan share something, that any material that he was discussing with you guys on this?
I think he sent a PDF. No, he gave us the book. He did not send the PDF.
Okay. I'll check. So, 1 second. No, he used this book, proof from the books, proofs, that book, right?
Yes, sir.
Okay. Just. Okay. So can you see my screen?
Yes, sir.
Yeah. Okay. So this is where you wanted to pick 4.5, right?
Yes, sir.
So when you pick 4, let's say if you pick 5, right? Something larger than 4.5, then what will happen? What change will happen? Instead of the 65, 64, you'll get, this p cube you are taking common. Okay. So from equation 5, you're taking common p cube, right?
Yes.
Okay, you got the 64. I mean, what I'm trying to say, it will only change this thing by a constant factor. Okay, you can take this to be 10. You'll get 1,000 or something like that.
Yes.
Won't be a very significant difference in terms of these parameters m and n.
Right, the order will remain same.
Order will remain same. So usually what happens is that constant factors are important, okay, but we tend to more focus on the parameters m and n. Okay, so what you can do is that you can artificially sometimes blow up the graph, and then this constant will just not matter. Okay. So
Like I thought we were trying to find an inequality rather than just the order of inequality.
Yeah. So yeah. You're trying to find an inequality. Okay, you got an inequality. Fine. But then after this, you have to think what terms are the important terms in this inequality. Okay. So there is this term m cube, there is this term n cube, right? And there is this term 1 by 64. So you have to ask yourself, how important is this 1 by 64? Okay. Is it I mean, it is definitely important. It's there. I mean, some special cases might not work if this if this 1 by 64 factor is not there. But perhaps it is not the most interesting part of this inequality, right? So so what I want to say is that, okay, let's look at this inequality. This chromatic number of G, where G is a planar graph, is at least this quantity. Okay. There is some proof that we discussed sometime in one of our previous discussions. Okay. So you know that chromatic number, I mean, this quantity is an integer. It is always going to be greater than 0. Okay. It will always be 1, 2, or 3. It will take some value like this, right?
Yes.
So, and ideally you want this thing to be large, right? Because you're lower bounding this quantity. So you want chromatic number to be large. Okay. And when you look at the right hand side of the lower bound, you want to ask yourself, for what values of m and n can this quantity be large? Okay. So this 1 by 64 factor is fixed here. Okay. So the case where it will be large is when m is very large compared to n, right? Intuitively.
Is
Yeah. So this 1 by 64 factor is actually not going to be very significant for you. Okay. So, I mean, if you let's say you chose instead of 1 by 64, you had 1 by 1000. Okay. So for a graph, if you are choosing m to be like, let's say 4n, now you will choose m to be 10n, and you'll get the same bounds, same lower bounds. Does this make sense?
Sir, I completely agree. The order is same and the constant isn't that worthy in an asymptotic sense. The thing was, I did not expect that this was an asymptotic proof. I was thinking this is just finding the maximum possible bound.
So, I mean, so this is after all an inequality, no? You cannot say that this is the maximum possible.
Maximum possible, like, I agree. This is not of course, this is not the best possible bound. But given that probabilistic equation, the least I could do is maximize equation 5 with respect to P. Right?
Yeah, that completely makes sense. Yeah. So if you're trying to maximize this, yeah.
That is what I did.
That is completely fine. I mean, this is the way to go. You ideally want to maximize this side. Okay? And
yeah, that's exactly what I did, and I obtained 4.5 n over m.
Sure. That is fine. That is completely fine.
And like,
yeah, that is the way to go. But after that, after when you have 4.5, then you might want to see that, okay, maybe like we can live with something without, we might not have to go into that calculation also. Okay. So
there was one minor problem, that 4.5 n over m might be greater than 1. In that case, p equal to 1 was the best bound with this equation.
So yeah, I mean, okay, so I got what you're trying to say. So the optimum that you are getting here, okay, for that p might be greater than 1, because this bound does not ensure bound given. I got what you're trying to say. So in that case, we'll have to stick with this value, right?
No, in that case, we can set p equal to 1. That will be the best bound. Because so if you graph this function, it has a peak at p equal to 4.5 n over m, and then it like uniformly reduces. Okay, that doesn't make sense, uniformly reducing, but basically it looks like a bell curve. So
Yeah. So okay. See, what I'm trying to say is that it, as long as this right hand side of this inequality makes sense. Okay. So you can try to optimize it. You can try to find the best value, but at the end of the day, uh, and I think, and that is the correct way to go about it. Okay. So as long as you are getting constants, I think are also required, but yeah, it won't matter much. So
yeah,
this is all about
I,
asymptotic M and N.
I completely agree with that.
Yeah. But yeah, that is the correct way to go. If you have an inequality, a lower bound on some quantity, then you want to maximize the right hand side, and whatever you obtain, you want to check whether it makes sense or not. Okay. And in which range it makes sense. Like here in this case, you wanted to get a probability. So like you said that 4.5 and M might be larger. So things like that. Yeah, you have to make sense of the right hand side. Yeah, try to maximize it. So the things that we are talking about, like these, in some cases, these might break also, right? So yeah, so what you are telling makes complete sense. Okay.
Yes.
Sir, I understood that if we maximize the right hand side with respect to P, then P equal to 4.5 N by M will maximize it. But uh, can you please explain again why we are not taking 4.5 and taking 4 once more?
Yeah. So the thing is that this P is a probability, right? So it has to be between 0 and 1. Okay.
Yes, sir.
So what is the bound that we know for planar graphs in terms of M and N? Must be written somewhere here. You guys remember, then you can help me out. Where is that bound? Okay, let's forget about that. So let's say for the best thing that you could obtain here by solving this equation. Yes, so this equation assumes nothing about from where you have got these quantities, right? This is an equation in, you're solving for P, you're maximizing P, choosing P to maximize this quantity. Okay, so this process of maximization has nothing to do with the fact that you are going to interpret P as a probability, okay, or like M and N are coming from a graph. It has nothing to do with that. It's just an equation that you're solving. When you solve that, let's say you get 4.5 N by M, okay, right? And for it might be possible that for some graphs 4.5 N by M is larger than 1. Okay.
But it may happen for 4 also.
It may happen, yeah. Then in that case, you'll choose P to be 1 as he was saying. Sorry, I mean I can't. I'm looking at the screen and I can't look at your names. Sorry. So yeah. So if that happens, then you just set P to be 1. Okay. Right. So look at this the way again that was being discussed. Look at what kind of function this is of P. If you want to be very precise, right? So you plot this thing as a function of P. Okay. Right. You set your limits that P can be between 0 and 1.
Okay.
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 And then you choose now you have a set of constraints. Okay. You have an equation. This is your objective. Okay. That you want to maximize. Right.
Yes.
You plot this as a function of P. Fine. But now you are constrained that P is a probability. So P can be between 0 and 1. Okay. So in your first plot, you plot P that you have to just make sure that you want to have P between 0 and 1. And then whatever feasible value of P is there that maximizes this, you just pick that value. Okay. Is this clear?
Yes.
Yeah. But what I really want you guys to get from this is that while this is the correct way to do it, okay, and you can solve it in this case, but this might not always be true. This equation might not be so easy to solve later on. There might be cases where you just can't figure this out, and you'll have to settle with a weaker lower bound. So I just want you guys to be comfortable with this fact that, okay, although 4.5 n by m is the way to go, that is the correct way to solve this, but 4 n by m is also fine. Okay. Does this make sense?
Yes.
Yeah. So this thing, like this RHS might not always be in this such a nice form, no, that you can optimize for it and solve it. Okay. So you'll have to work with lower bounds, some weaker lower bounds. So yeah. Fine.
Yes, sir.
Yeah. Okay. So the other guy who was also telling the same things, is this okay?
Yes, sir.
We can talk more about it if you want, but let's move ahead now. Okay. Okay. So there was this one section of the book that that you guys wanted to discuss. Okay, 6.7 on DP. So I'll discuss this a little bit, and if you have some questions in mind, you can yeah, just take a note of them, and you can tell me after we finish a couple of units. So we'll be talking about sequence alignment, okay, and how to do it in small linear amount of space. So these things will make sense when I start describing the algorithm. So let's go ahead. Yeah. Okay, so we are first looking at sequence alignment problem. Okay, it's dynamic programming. So how many of you have like already read this and are very comfortable with this? So come on, tell me.
Sir, I read it, but I have not confidence that I am very comfortable.
Okay, sure. So you have some idea, no, of this problem? What the problem is? What the setup is? Everyone? Or
So the sequence alignment part was okay, but that space complexity part was not. Like we are not very comfortable with it.
okay, sure. So should we go over the entire thing a bit slowly, or should I quickly go over the sequence alignment part and then spend more time in the space saving part? Okay, let's go over it slowly. Okay? So, right. So this string similarity. Okay, so I'm using these slides which I'll send you. Right. So this is the textbook that we are using, Kleinberg and Tardos. These are the accompanying slides for this. I'll send this to you later on. Okay. So the problem is you're giving two strings. So input is two strings, and you want to figure out how similar they are. Okay. Of course, we need to define the notion of similarity. Okay. Let's first take some examples. So you're given now these two strings. So one is this string occurrence. So this is like two misspelled words of occurrence. So I think this one is correct. And you want to say that how much similar these things are. Okay. So here are three tries that are there in this slide. So you have this first word, you have the second word. You match each of them, each of the positions perfectly. Okay. I mean, the way in that occur, you don't give any gaps in between. You observe that one of the strings was longer than the other, so there is a mismatch here. Okay, the special kind of mismatch called gap. So this accounts for one gap, and at other places which are light, which are gray, there are all mismatches. So in this try, you have 6 mismatches and one gap. Okay. Now you try another setting, like you see that, okay, if I put a gap over here, then I just get one gap and one mismatch. So perhaps this is a better way to say that, okay, this is these two strings are close, right? And then there is 0 mismatch and 3 gaps. So there is one more way you can do it, so that there are mismatches and gaps. So what follows, you have a cost for each gap and cost for each mismatch. Okay, so you have a penalty that you have for each gap that you have. So like this is a gap, so you get a penalty for the gap. Okay, and you get a mismatch penalty. Okay, so I'll explain the subscripts here. But now there are two mismatches here, and you get this penalty mismatch for. Okay, but for us, we'll consider this mismatch to be just. I mean, it is not going to depend on which alphabets are mismatched. For us, it's going to be the same number alpha. But a lot of motivation for this comes from this genes and bioinformatics kind of things, where these A, G, C, T. So they actually pay penalty depending on which of the characters have mismatched. But for us, we are going to assume that this is going. Okay, this is their assumption. For us, we'll assume that this is going to be alpha. Okay, so if there is a gap, there is a cost of delta. Otherwise, there is a cost of alpha. Okay, right? And our goal. Let's come to this later on. So our goal is what? We want to match the strings, given strings, such that the total penalty is minimized. Well, penalty is measured by, so if you have like 3 gaps, you will do 3 into delta, 0 mismatch plus 0 into alpha. Okay, and here it's going to be alpha plus delta, and here it will be 6 alpha plus delta. Okay, so this is going to be the penalty, and you want to come up with the best matching of the two strings. Okay, in terms of that the cost that the penalty is minimized. So the problem statement clear?
Yes, sir.
So the problem statement again, I'll just go over it quickly. Input is 2 strings. Okay, goal is to come up with a matching that minimizes the penalty. Fine.
Yes, sir.
Yeah. Okay, so this is one of the slides that is here. I'll send you a mail. You can check it out. Like this is a motivational thing. Let's move ahead. So like this is a quiz for us. So these are the 2 strings. Okay, assume that the gap penalty is 2 and mismatches penalty of 2 is 2. So what is the best matching that you can come up with these strings? So what is the cost of the best matching? So there are 5 options. So come on, anyone can just tell the answer as soon as they figure it out. Sorry?
So 3, I think.
3. Okay, okay. Any other tries?
Sir, I also think it's 3.
It's 3. Okay, okay. So let me go. Actually, when I looked at it, I thought it was 1. So let's see. Oh, is it 3? So
but
these
it can't
first
be 1
3
since
you will
at
have to
least
match, no?
1 gap has,
Tell me.
like it can't be less than 2 because at least 1 gap has to be there. The number of
Sure.
letters is different.
Right, you're right. So these first 3 you have to match. Okay. Is it fine?
Yes, sir.
And then you better match these last 2. So okay, I guess, yeah, 2 for a gap and 1 for a mismatch, right? So 3.
Yes, sir.
So is everybody fine with this?
Yes, sir.
So let's look at this dynamic programming algorithm to solve this, right? Okay, so here's the formal problem statement. Let's go over this slide once. So there are 2 strings, x1 to x. Now these are 2 strings. They might not be of the same length. Okay, gaps are also there. So x1 to xm and y1 to yn are 2 strings, and we want to find the smallest cost alignment of those strings. Okay, so an alignment is just a matching. Fine. So like we can look at the definition, but let's look at this example instead. So this is a string x1 to x6. This is another string y1 to y6. So what is the alignment in this case? So x1 does not get matched with anything. Okay, so we are not going to, and this is the list of the matching. So it's matching, and we are going to define it. X1 is not getting matched with anything, so we have left that empty. X2 gets matched with y1. Okay. Achha, can you see my mouse pointer? So
Yes, sir.
okay, good. X3 gets matched with y2. Okay, and so on. So what we are talking about intuitively, we have just given it a definition. We have called it an alignment, and I think this makes sense. And cost is going to be the total number. Again, we are going to, for us, alpha is going to be fixed. Okay, so it's going to be total number of mismatches plus total gaps. Okay, fine. So in this case, there are 2 gaps and there is 1 mismatch, right? And our goal is to come up with a minimum cost alignment. Fine. Now I'm going to go to the algorithm of this. Problem statement is clear to everyone. You can stop and ask. This is a good time to clarify the problem statement, because the next thing is also going to be the next. The space saving algorithm is also going to be for the same problem. So it's very important at this point for all of us to make sure that the problem statement is clear. Anybody has any questions? Okay, then I'm moving ahead. Okay, now let's look at the algorithm for this problem. Okay. So we are not going to describe the algorithm just yet. Okay. So the first step, as in many DP algorithms, by DP I mean dynamic programming, is to write the optimum. As a you want to express the optimum of the solution of that problem in terms of the optimum solution of its subproblems. Okay. So this is our first goal, right? And now this is again a bit of notation, but I'll define this once. We'll look at an example and I'll come back to this. Okay. So opt ij is the best alignment that you can do for strings x1 to xi and y1 to yj. Okay. So recall that your string x1 was a m-bit string and x was an m-bit string and y was an n-bit string. Okay. You want to say that opt ij is the best possible that you can do when you match till ith position of x and jth position of y. Okay. So let's see, like if I is 2 and j is 1, okay, then you want to say that, okay, I'm matching x1, x2 and y1. I'm only interested in solving this part of the problem. I don't care about the rest of the problem. So what is the best matching? By best matching, I mean what is the minimum cost alignment that you get? Okay. So that is going to be a opt 2 1, right? And then you define opt ij for in general. And what is your goal? You want to find opt mn. Okay. Again, x is the m-bit string and y is the n-bit string. Fine. Now see. Now let's look at this thing. Opt ij. Okay, when you are matching till I and j, then what all things can happen? Okay, we are interested in the indices xi and yj. These are the last points. Okay, so what all things can happen? So your output, either they are like discussed, there are 3 cases. So first case is that your output matches xi and yj. Okay, your output says that, okay, this xi and yj is going to be in my alignment. For example, just look at this. Okay, so let's say I was 5 and j was 4. Okay, and so let's look at this this bit. So we are looking at opt 5 4. Okay, and what our output does, our algorithm matches x5 and y4. Okay, so x5 and y4 are present in our matching, right? So if this happens, then there are several cases, right? Either there is a mismatch and you pay for that mismatch. So your algorithm matched 5 and 4 here, right? And there was a mismatch. So this is one of the cases possible. Okay. Other case that is possible is that there is no mismatch. Right? So there are several cases. So we'll consider all of them. So either there's a matching and you pay for that mismatch. Okay. You pay for that mismatch, and in addition, for the rest of the string, you'll also have to pay for the cost that is there in the optimum matching of the rest of the string, right? Till indices I minus 1 and j minus 1. Is this thing clear? Case 1?
Yes.
Please stop and ask any questions. Okay. So this is one of the possibilities. The other possibility is that in the optimum matching till xi and yj in these strings, xi is left unmatched. Okay, so this is the second case here. Okay, let's say this is like this case. In this case, y is left unmatched, but like this is going to be the so here we are in case 2b, yj is left unmatched. So for us, if j was 5 and if this was the optimum matching, then y5 is left unmatched. Okay? And then you have to pay the corresponding cost. You have to pay the gap cost for y, right? Additionally, you have to pay the best. You have to pay the optimum cost till for the rest of the string. Okay. So let's say again, let's look at this case when our index was 5 and y5 was left unmatched. Now in the string y1 to y4 and x1 to f4, by assumption we have found the optimum matching. Okay, so for that the cost is going to be opt of 5 4. Fine.
Yes, sir.
Okay, so I hope it's clear. We'll go over it again. So yeah, so let's look at this opt of ij. Okay, I'm looking at this quantity now. I'm not in, these are two base cases. Okay, I'm not going to focus on them. Fine, these are base cases. You can verify later on. So opt of ij, the best possible solution for matching till index I and j in strings x1 in strings x and y is what? Okay, there are 3 cases and you want to choose minimum of the 3 cases. Okay, so these are the only 3 possibilities, and when you choose the smallest of them, okay, you find the optimum solution for the ith and jth case. Okay, so what is the first possibility that happens? First possibility is that when you match xi and yj. Okay, the first possibility. So this is this case. Okay, when you're matching xi and yj, or this case. Okay, when you're matching them. Okay, so when you match xi and yj, right, then you have to pay the cost, mismatching costs. Okay. So if xi is not equal to yj, then you'll have to pay alpha, else this will be 0. Okay, so that's good. And so this is one cost that you'll have to pay. And so this cost is just for the index I and j, right? And for the rest of the thing, by assumption, you are matching it optimally. So you'll have to pay this additional cost. Okay, so this is one of the possibilities that might happen. Other possibility that might be is that you're not matching xi. Okay, you're leaving xi unmatched. For this, you have to pay a gap cost for xi, right? And the optimum cost for matching the rest of the string. And the third case is that when you're not matching y, j. Okay, in this case again you're going to pay the gap cost plus the additional cost for optimally matching the rest of the string. Okay, is this formulation clear?
Yes, sir.
Okay, go over it once more. So I think, yeah, so I'll proceed now. Okay, and then you have this algorithm. Okay, so this algorithm is again very I think it's much more easier to look at this algorithm in an example. Okay, so now these are your 2 strings. So one is similarity, okay, and other is identity, and you want to compare their you want to come up with the minimum cost alignment for these strings. Okay, and there is some alpha and delta that I'm not interested in right now. Okay, so let's solve this. I mean, these are some constants, so we can figure it out, right? By the recursion. Since we are filling this table, we can look at this value and say, okay, now this is going to be alpha, this is going to be delta. Like look at 2 of them and solve them. But I'm not going to do that. Okay. Let's look at overall how the algorithm works. Okay. So let's say you are in. So okay, and also let me tell you what is going to be the entry in each of these cells. Okay, so the entry here is opt ij. Fine. So at this, and this is n cross n matrix indexed by the length of the strings. So at each entry is going to be opt ij. So when the length is 0 of the strings, when there is nothing to match, right? You just put this quantity to be 0. Okay, when this is 0 and this is s, you put some cost, some constants that you believe are the true case. Okay, so now I want to look at one of the entries of the string. Okay, I'm looking at this entry 4. When you want to match I and j, it does not matter what these cells are, but this quantity is going to be minimum of these 3 quantities. Okay, so let's go over there. Okay, so now look at this entry, ijth entry of the matrix. Okay, so the ijth entry of this matrix is, you look at the 3 of the neighbors of this matrix. Okay, so let's say I was here. Okay, I'll look at 3 neighbors of this matrix, 1, 2, 3. Okay, this neighbor corresponds to I minus 1, j minus 1. This corresponds to, I minus 1, j, and this corresponds to ij minus 1. I look at these 3 entries and I add the corresponding cost. Okay, whichever is minimum, I choose that cost. Fine. Does this make sense?
Yes.
Right, and you do that and you fill this table. You start here, you are at 0. Okay, you know this value, you know this value. These are the base cases that you have. Assume that they're given to you. Okay, for this entry, you look at these 3 matrices. Okay, and you say that, okay, this will cost me this much. If I start from here, then I'll have to pay delta. This is the mismatching one. Delta, you have to pay for the gap cost, right? And alpha, you'll have to pay for the mismatching cost. So the point is that you can fill this entire matrix by looking at if you want to fill a particular entry, all you want is that the neighbors, these 3 neighbors of this cell, of this entry of the matrix are filled, and you can fill the entire matrix. Okay, is this clear?
Yes.
Fine. So let's say you fill this matrix, right? And where will be the optimum cost after filling this matrix? Where will you find the optimum cost?
Last entry.
So what is that in this case?
7.
7. Okay, fine. So this is going to be your optimum, right? Did you understand this? Did everybody understand this? That
Yes,
the
sir.
optimum is here?
Yes, sir.
So
Yeah. Okay.
Sir, in
why
this
is
case,
the
for
optimum less than all 3 of its neighbors?
yeah, same question.
So in this case, so let's say just assume that all these 3 were filled. Okay, before you came here, right? Then you can fill this entry by looking at these 3 cells and the corresponding costs.
No, but my formula says that the cost always increases as I go from I minus 1 comma j to I comma j, or any iterations of that.
So your algorithm says that your cost always increases as you go from.
From like I minus 1 comma j minus 1 to ij, or I minus 1 comma j to ij, or option. Basically, all 3 alpha, basically alpha and delta both are positive. So Mij should be greater than all 3 of its neighbors.
Yeah, that is correct.
So in this case, if the letters are
I think-
same, do they have negative alpha?
No,
Then
no.
it makes sense.
They don't have negative alpha.
But only then it makes sense. Otherwise,
Yeah, I think, I mean, I know what is happening. 1 second. Let's go to the textbook here. Okay. So what this graph is doing is that they are looking at the minimum cost path. So Oh, so you look, can you see this figure 6.18?
Yes.
Hmm.
So we can see like every entry is at least as big as one of its neighbors.
Every entry is at least as big as one of its neighbors. Yeah. What is happening here? Is this the case? Should always also be true, right?
I think what Rohit said is the only possible option. Alpha II must be negative.
But this is not the case. This should not be the case. So this recurrence makes sense, okay? And what we were looking at here, that makes sense. Fine. Okay, then let's look at this one for now. Okay, so this is also putting opt value here, right? So they are building the matrix starting from here. In this one, the matrix was getting built starting from the top corner. They're building it from bottom corner. Does not matter. Okay. So yeah. So if you are this at this one entry, right? So yeah. One second. One second. Hmm. Yeah. So okay, this thing is fine. I mean, this has to be fine. That if when you want to move to an entry, okay, you just look at the three of its neighbors and move according to the corresponding cost. Okay. But like you said, this is an issue, right? Because this one, okay, how do you get this? Unless you have
So if we look at the 2,3 entry, so we are, so first of all, obviously delta is equal to 2. That much is clear, right? So if we look at the 2,3 entry, that is we are matching SI and I. That has a value of 1. And obviously the best matching for SI and I has to be I matched with I and S matched with the blank. So since I already know that the blank has a cost of 2, I must have a cost of -1.
okay. Let's not get into this detail for now. Okay, I'll get back to you guys on this. Fine. This will take a lot of time of us. I'll get back to you on how this matrix or what does this mean. Okay. For now, just whatever the logical thing that we were talking about, assume that that has to be true. So this entry, just forget about this for now. I mean, this might have some other interpretation that I'll get back to you. Okay. So assume that an entry, mith entry, is filled by looking at the three of its neighbors. Okay, you look at the three of its neighbors and look at which of the costs is going to be minimum. Okay. When you move from the neighbors to that. So this thing is clear, right?
Yes.
Let's worry about this later on. Okay. And let's also assume alpha to be positive for now. Fine. This I'll have to check. What does this mean? In any case, when you solve it, then the correct answer is going to be at the bottom right corner of this table. Okay. Fine.
Yes, sir.
And now you want to find out. So this just gives you a value. It does not give you what the alignment was, right? So if you want to find out what the alignment is, then the idea is that you can just trace back. You can just go back to your solution. Okay. So at this entry, you find out from which of its neighbors you got this value. Okay. So that must be a part of the solution. When you have this, then you find out from which of its neighbors you got this value. How did you come here? You must have come here from one of its 3 neighbors. You find out from which of them. Okay, you go to that neighbor. Similarly, at this point, you find out from which of its neighbors you got this value. You go there. Okay, and then you repeat. Okay.
Yes.
Yeah, and regarding this entry, I'll check this later on and I'll send you guys an email. Fine. Yeah. But whatever this thing that the recursion that we have, okay, or the formulation that we have, that is correct. You don't have to worry about that. Rest how the entries are there and what values of alpha are there or not, that is a different question. Okay. I think alpha should be positive. Does not make sense to have negative cost, but yeah, I mean, it's okay. Like if you have negative cost, then also this should work. Okay. So the assumption that alpha is greater than 0 is not written explicitly at any place. Fine. So is this algorithm clear? And how you are filling the table, that is clear. So there is a confusion that, okay, what is the value of alpha? Why is this negative? Like, why is this falling? That aside, other things are clear, right?
Yes.
So let's move ahead. Okay, so if you fill this table, this is an M cross N matrix, right? Then what is the time and space that you need? Okay, let's calculate that. So how much time do you have to spend in each cell? You just have to look at 3 of its neighbors, okay, and then find the best one from the neighbor, from 3 of its neighbors, right? So in each cell, you are going to spend a constant amount of time, right? And there are M into N such cells. Fine.
Yes, sir.
So the time is order of M into N. Okay. But now what you did here is that you also gave M into N space. Just because the size of this matrix is M times N, you allocated M into N space. You want to save on that. Fine. So this next algorithm, okay. Okay, so this is okay, let's go to this a little bit. So both M into N time and space are required. It's very easy to see. And okay, so this is an interesting thing. So did you guys have your lectures on complexity side, P and P?
Yes, sir.
So it says that this problem, okay, so let's say M equal to N, fine. So the running time is going to be N square, right? When M equal to N, then the running time is order N square, right? So this says that if you can solve it even in a little bit better time, okay, then you have a huge improvement in solving a very hard NP complete problem. It's NP complete, so it's not correct to say very hard, but you can prove something major for solving an NP complete problem. So even a slight improvement in this algorithm is going to be a breakthrough. Assume M equal to N. Okay, so very interesting problem. So I mean, very simple, but it has other connections. And this algorithm is very trivial, right? I mean, there was nothing. You just, when you realize that how you are going to fill an entry, okay, you are just going to look at 3 of its neighbors and update that. Then improving this algorithm, then it might occur to you that, okay, people who are working on this and research, they might have been able to improve it, but turns out that you see that this is not too far away from now. It's 2015. Okay, so yeah, so very interesting. You guys should check this out. And okay, so now what we want to do is that this also uses order m into n space. Fine, and we want to get rid of this much space usage. Okay. So I'm not going to discuss this one now because I think we already spent a lot of time here. Let's go to the space saving algorithm. Okay. So the algorithm that we are now going to look at is going to solve the same problem that we talked about last time. The time complexity is not going to change, but the space, we are going to reduce the space from m into n to m plus n. Okay. So if m was equal to n, so the initial algorithm was taking space n square. Now it will take space order n. So it will be a quadratic improvement over space. So that's what we are going to show now. Okay. So goal clear?
Yes.
Okay. So let's look at this algorithm first. Edit distance. The algorithm that we discussed last. Okay. So you saw that in order to compute the optimum at this ijth entry of the last matrix, right? You looked at the 3 of its neighbors. Okay, and then you chose the one such that the value here plus this, and you chose to minimize over. So you took minimum over these 3 quantities. The value that you had over at this node plus delta, the value that you had at this node plus this quantity alpha, the value that you had here plus this quantity delta, right? And you computed the value here. Okay, so that was a matrix. Now let's look at this graph. Okay, so again, like graph is inspired from the matrix. So at the way that you fill an ijth entry is by looking at the 3 adjacent cells of a matrix. So you take the matrix that you had initially and you define a graph from that matrix. Every cell of that matrix is going to be a node. Okay, and the edges, the directed edges, are going to be the entries on which the value of this matrix, this entry depends. So the value of this entry, or ijth entry of the matrix that we saw earlier, depended on these 3 of the neighbors. So the only edges that are coming into this node are from the 3 of its neighbors that we talked about. Okay, so is this definition of this graph clear to everyone? Okay, to make a graph, you need to define vertices and edges. We are making a directed graph. Okay, so the vertices are the entries of these matrices. So this is an m cross n matrix. So vertices are the entries of these matrix, or the ijth entries of this matrix, each cell of the matrix. Okay, so is the vertices clear to everyone? What the vertices of this graph is?
Yes.
Now we need to define the edges. Okay, this is a directed graph. I'm going to define the incoming edges or the for each of the vertex. So let's look at the ijth node of this graph. Remember that this corresponds to the matrix that we talked about before. Okay, in order to fill this entry, we looked at only 3 of the adjacent neighbors of this cell in the matrix, right? So the value here depends only on 3 of its neighbors. So we are just going to put 3 edges here. Okay, so use that matrix to define this graph. Is the definition of graph clear to everyone? Should I repeat?
It's fine.
Please repeat
Can see.
the edge part.
It's fine. Okay. Now you look at this
Sir,
graph.
can you please repeat the edge part?
Yeah. Sure. Okay. So this matrix thing was clear, no? That we talked about before,
Yes, sir.
right? And now I want to define a graph using this matrix. To define a graph, I need to define the vertices and I need to define the edges, right? So first step is to define the vertices. So each vertex of the graph that we are going to define is going to be corresponding to every cell in this matrix. So there are m into n cells in this matrix. So there will be m into n vertices in the graph that we are going to define. Fine.
M plus 1
One
into M plus
corresponding.
1.
Sorry.
Since we have one extra row and column, shouldn't it be M
Sure,
plus
sure,
1
sure,
M
sure.
plus 1?
M plus 1 into n plus 1. Sure. M plus 1 into n plus 1 vertices. Okay.
Okay, sir.
And now we want to define the edges in the graph after defining the vertices. Okay. So every vertex, now think of this as a vertex in a graph. Okay. So think of each cell as a vertex in the graph, but you have not put the edges till now. Okay. So how will you put the edges? You know that this and this vertex only depends on these three of its neighbors. Okay. Fine.
Yes.
So put an edge. So put an start an edge here. Put an edge to this vertex. Start an edge here. Put an edge to this vertex. Start an edge here. Put an edge to this vertex. And you complete all the incoming edges of this vertex. That's how you define the edges. So it's shown here. Is it okay?
And these alpha and delta are weights.
Yeah. Alpha and delta are the costs. So at ijth entry. Okay, so what is this entry? This is I minus 1j.
Yes, sir.
So if you at I minus to move from I minus 1th I minus 1j entry to ij entry, you have to pay a cost of delta. This says that you did not match the ith entry of xi. Okay. I mean, you have to go back now to recall all these things.
Okay, sir.
I know. I mean, we've been talking these things for what an hour now, so it might be difficult. But just for now, just keep this picture in mind. Okay. Just keep in mind that this entry depends on these three, and each of them, of course, has their own value. You look at them and choose the one that minimizes, and you fill this value. Okay. Is this fine?
Yes, sir.
Mm-hmm. Right. So now let's look at this graph. Okay. Now we're going to work on this graph, and our goal is to minimize space while keeping the runtime order m into n. Okay. So first of all, we define this following quantity f of ij. Okay. So you start from 0, 0. And you look at ij. F of ij is the length of the shortest path from 0, 0 to ij. Okay, so what is the length of this part? I mean, this graph is a weighted. All these edges have their own weights also. Okay, so you start from here. Otherwise, if the edges don't have weight, then length of any path from here to here is going to be same, right? I mean, you just have to move these many units horizontal and these many units downwards. That's going to be your length in this graph. Okay, but the graph that we are looking at is a weighted edge graph. So each of these edges is going to have its weight. Okay, so for example, what is going to be the weight between this edge and this edge?
Delta.
This is going to be delta. What is going to be the weight between this edge and this edge?
Delta.
No. Yeah, this is going to be deltas. And this one?
Alpha x2 y2.
Alpha x2 y2. Yeah. So you have filled. Now this is a weighted graph, and you look at the length of the shortest path from here to here. Okay. And that is going to be your optimum by definition. I'll leave this for you guys to check it out. This is the same thing that we have been talking about before. but you're just defining them, those things in the language of a graph to make the arguments that come later on a bit easier. Okay, is this clear?
Yes, sir.
Yes, sir.
So okay, now they have proved it. I mean, you can look at this proof later on. I'm not going to go over it. The proof does not actually need a proof. Still, if you want an argument, it's here. I'll send this slides to you anyways. Okay. For now, if you are not able to see or not able to, you're not convinced with this, just let us assume that the length of the shortest path in this graph, okay, is the optimum value at this point. Okay, is it okay?
Yes, sir.
Yeah. So now let's look at this other part of this problem. So you defined a function fij, right? Okay, I'm not going to on the computation part till now. Okay, but I just want to define one more function gij. Now let's say you start at the node ij. Okay, then gij is the length of the shortest path from ij to mn, whatever path this is, some path. Gij is the length of the shortest path from ij to mn. Okay, what is your optimum? Optimum is length of the shortest path from 0, 0 to mn. Fine.
Yes, sir.
So what is the length of an optimum path? Now this is a question that I'm asking you guys. What is the length of an optimum path that starts at 0, 0, ends at mn, and passes ij? So recall you defined two functions, okay, f and g. So what is the length of the optimum path that starts at 0, 0, ends at mn, and passes through ij? Okay. What is it?
Fij plus gij.
Exactly, fij plus gij. Okay. So this will be there somewhere. So by definition, fij was length of the optimum path from 0, 0 to ij. And by definition, length of the optimum path from ij to mn is gij. Okay. So fij plus gij is the length of the optimum path from 0, 0 to mn that passes through ij. Fine. Okay. We'll come to the computation later on. First, so what I'm trying to do first is without computing any runtime or anything, I just want to describe you how to solve this problem. Okay, how to divide this problem into sub problems, and then we'll compute the runtime and all other things. Okay. But let me just mention this since we are already in this slide. So this fij, this function, okay, we can compute this function in order m into n time and order m plus n space. So can you tell me why? Why can you compute this function in this much space? Okay. So let's say I give you I tell you, okay, this is the row that I want you to fill. Okay. And I want you to do this in this much time and this much space. How will you do it? The key thing to look at it is space. If there was no constraint in space, then we saw earlier, you can fill this entire thing in order mn time and order mn space. Right? How much space do you need now? If I tell you just to fill this column, nothing else, fill the jth column, how much space will you need? Any guesses? Any ideas?
Can we use this Castras?
Huh? Sorry, can you repeat?
This Castra algorithm.
Yeah, I mean, a simple observation that you can, like what I have been trying to stress, and this observation is that the value at each point of each vertex depends only on a small locality of its neighbors. Okay, so it's not that, like, if I want to fill the value at ij, I just have to know the value at these three places, and then that is good enough for me. Okay, right? So if I want to fill this column, okay, so assume that this column is fixed. So this is a base case, we'll fill it beforehand. Okay. Assume that this column is already filled. How will I fill this column? Can I fill this column now? If I know the value, all the values in this column, can I fill this? Of course I can fill, no? I can fill this value, okay?
Yes, sir.
I can fill, after I know this value is already known, I can fill this value, okay? Then I look at this value I just filled, these two were already given to me, I can fill this value. And similarly, I can fill this value, okay? So I can fill this entire column, right? Let's move to the next column. Now, do I need to store the first column in order to fill this column? No, right? I just need to know the one column that is next to it, right? This column is already filled. I just need to remember this column now. I can throw away this column. So the space that I was using to store the values in this column, okay, I can reuse that space. I can throw away these values and fill in these new values. So I've reused space. The thing, like the difference between space and time is that space you can reuse, okay, in computation. Time, once you have spent, so I mean those many operations are gone, cannot reuse them. Fine. Did you understand this?
Yes, sir.
So whenever I am filling any column, just knowing one column before that is sufficient for me, right? Knowing the values in one column before that is sufficient for me. So if you want to be more precise, then we are going to just store these, we'll just keep two columns into account in terms of space. I'll store first these two columns. Okay, these values are known to me, these values are not known to me. Looking at these values, I'll fill these values. Okay, then I'll throw away this column. I'll now store these two columns, y1 and y2. y1 is known to me, y2 is not known to me. I'll fill y2 using y1. I'll do the same thing for y3. Okay. So how much at any point, I'm not using more than a column number of spaces. Okay, I'm not storing more than twice a column, let's say, right? Fine. So any column I can fill by using a very small amount of space, order m space. In fact. Does this make sense to everyone? Okay, recall, like the problem was I just wanted you to fill this column. Okay, and this I said you could do in, I'm not telling you to fill everything here, okay? I'm not telling, if I told you to fill all these things, then the space itself is m into n. Space is large, but I don't want you to do that. I just want you to fill one column. That you can do in very small amount of space. You can forget about all the values that came here. Okay, fine.
Yes, sir.
So this I'll leave you to check. If it's not clear, then you can ask any questions. So if some specific questions, it's even better. But okay, I'll leave this one at that. So again, was there any questions?
No, sir.
Okay, okay, I'll move it. Okay, so now you saw how to calculate this, right? At this thing, the way you calculated here, same thing you can do for Gij. Okay, any index Gij you can calculate in a similar way. So remember, Gij was the length of the shortest path from ij to mn. Okay, so you can calculate Gij also in a similar way. Okay, fine. Now let's look at the divide and conquer part. So this is something that you guys have already told me. Okay, length of the shortest path from 0 to mn that uses ij has length fij plus gij. Okay, this is something that you have already told me. Already looked at this. Now let's look at how to divide this problem into smaller subproblems. Okay. Now let's look at the optimum solution. And now since we are talking about a graph, and we have understood how we have already reduced this problem to finding the smallest path in graph. We are no longer talking about the string problem now. We are just talking about a graph problem. Okay. So you want to find the shortest path from 0, 0 to Mn. Okay. Right. That path must cross every layer. By layer, I mean a column. That path must cross some vertex in every column. Right. Is that clear?
Yes, sir.
Sure. Pick the column, pick the middle column. You want to divide this problem evenly. Pick the middle column. Okay.
Yes.
Yeah. So now observe that you can fill the entries of this middle column using very little amount of space, order m space that we talked about before. Okay.
Yes.
I want to calculate Fij, okay, for every entry in this column. This I can do using order m space. Is this clear? So let's talk about like this. This is the only part that is required here. Only calculation part that is required. Rest, I'll not be doing any calculations. But this I want everyone to understand. Okay. This thing, this slide. Let's look at this slide. Okay, so Fij is the length of the shortest path in this directed weighted graph. This is length of the shortest path from 0, 0 to ij. Okay, forget about the second line. I give you a column. I give you a jth column, and I want you to fill the value of f star j. I want you to fill this entire column with the value Fij. Okay, so like f1j, f2j, Fij, fnj. Okay, mj. So can you do this? Can you fill this entire column in order m plus n space? So this is the only way we are saving space. Okay. So how can you do this?
Yes.
Is this clear to everyone?
Yes, sir.
So okay. Yeah. So just keep this in mind. If in case it's not clear, I'm sure it is. But in case it is not, just keep this in mind that we are going to fill just jth column with the values of Fij, and we can do this in linear space, order m plus n space. Okay. So now in the algorithm, what you do is that you use linear space to fill this column with Fijs. You use linear space to fill this column with Gijs. Recall that Gijs was just Fijs, but you started from a different direction. Okay. And then you find that index, okay, that minimizes this thing. You find an index Q that minimizes f of Q n by 2. I mean, let's say this is the index of interest Q. Okay, this is Q. You find such a Q, which might be anywhere, such that the length of the path from 0, 0 to Q and length of the path plus length of the path from Q to Mn is minimized. Okay, you know that this Q must lie in the optimal path. Is this point clear to everyone? So I'll repeat my argument. You want to find a shortest path from 0, 0 to Mn. Okay, you know that this path must cross every layer. No, this is connected. This path cannot skip any layer. Just look at this graph. In particular, this path must cross the n by 2 layer, right? Okay, so now I am interested in finding which vertex in the n by 2 layer does this path go through. Okay, to do that, I know that the vertex through which this optimum path will pass must satisfy. Let's call that vertex Q. Then this vertex must satisfy that the length of f from 0, 0 to Q plus length of the optimum path from Q to Mn must be small. This is the only way in which this can happen. Okay, is this clear?
Yes, sir.
So once this is clear, right, you have found this vertex q. Now you know that rest of your path. Now, but you just found one vertex in your path, right? You were supposed to find n of them, right? Or n, what is the number? N plus m, yeah, n plus m of them. So n of them here, m of them here. So n plus m of them you are supposed to find. You just found only one till now. Okay, but now observe what has happened. Now your problem has divided into two subparts. You know that the rest of the path cannot go below this, no? Rest of the path is restricted to this top column. Okay,
Yes.
and other part is restricted to this bottom graph, subgraph. Okay. Now you will recurse on these two subgraphs, right? Is the algorithm clear?
Yes, sir.
Okay. So once you do that, and then like it's already you are all of you are used to how to calculate running time. You write a recursive relation for the space, okay, and then you calculate it. Okay. I mean, space is simple because in each call you're using order m space. Okay. So you when you filled this, you used order m space, right? And then I mean, I'll leave this analysis to you, runtime and space and
Second line says only constant space is required.
So so this says that only constant space is needed to maintain per recursive call. So when you are here, you found this index, okay? Now you want to find the so what you're going to do is that you're going to save this space. You'll completely clear the space that you have and just save the location of this cell, okay? That will be one xi and y3, no? So like by constant means just this pointer to this cell you need to keep. Fine. And then you recurse. Is this clear? So let's say you have found this and found this cell q in the n by 2th layer. Fine. And you are before starting recursion. Now you look at how much space do I have? What is the budget of my space? You'll observe that you can get rid of all the entries that you had before, right? Everything that you saved before, you can completely delete all of those things and just keep this value, this pointer q. Okay, the entry of the location of this cell, right? Because now you're going to start on fresh sub problems. You don't care about what you had before. Okay. So when you start a recursive call, you don't need to store anything. Are you concerned about this, like whether it should be constant or should it be log m, these kind of things?
I thought.
What is the concern?
I thought it said that each recursive call, not storing. I was thinking about computing each recursive call. This is only about storing. So after the recursive call ends, I can just discard that m plus n graph, right?
Yeah. So this graph you are not storing at any point. Yeah.
So computation is m plus n, but storing is O1.
Storing is
Constant. After each recursive call. So each recursive call requires at least m plus n space. But after the program ends, I only need a constant space to store the result.
no, after the program ends. So can you elaborate this? So let's say I started with this. Okay. I found out this this index in the n by 2th column. Fine. And then I recursed on this left part and right part. These two have ended now. This is what you're telling, no?
Yeah, so finding the column is m plus n.
So finding the column is n plus m. Fine. Yeah.
But I can discard it. I only need a constant space after computing the minimum. So I can basically reuse that m plus n space.
Yes, yes, yes. So that is the entire point. So you are always reusing that space.
Got it.
Yeah. Like when you found out the entries of this column also, you reuse that space, no? You always maintained only 2 columns, like, or the previous column in your computation values in that column. You discarded the rest.
Yes.
Yeah. So that's why it's working out. Space, you can reuse space, but usually when you spend time running time, you cannot get that back already. Yeah. So I'll leave this calculation to you. So space and running time, but this is the main idea. Okay. So you want to just compute the vertices of this path. You divide this problem into subparts. Okay. To compute the division point, you need not spend much of space. Okay. And then your problem divides into 2 parts, and you recurse on each of them. Fine. So the only, I think, concern that is left today is about the entry of this matrix. I believe, like you guys have told, I think now that this should be negative, but I have to verify now. Okay. So this I'll do, right? But don't get confused by this matrix. Okay. This is a detail that I'll give to you guys. Okay. But I hope that this thing is clear. How you update the entries of this matrix is clear. Okay. This equation that is written here, this does not depend on what are the values of alpha. Like alpha xi, they are of course different. Delta can be different, can vary on each cell. Whatever these values are, okay, but the way you are going to update this is going to be the same, irrespective of the values of alphas and deltas. Okay. There are no constraints here on alpha and delta. That is definitely true. Okay.
Yes.
So the algorithm that we just said, does that have the same time complexity?
Yeah. Time complexity is same.
Hmm.
A bit more careful analysis is needed here. Okay. But yeah, you can check this thing. Time is same. Okay. So these are recursions that you have been solving throughout your course. That's why I'm not going to go into them. Are there any other questions that you want to discuss? Today time is over, but we can again meet. So any other thing? You can send an email, okay, to all of us. Saurav, Sayantan, Chandrima, and me. You can send an email. You can see if you guys want to meet. If you have any other questions, or just ask over classroom, and we'll try to see. Yeah, and so go through these things again. If there are some other problems or confusions, okay, especially in today's discussion, then let me know.
Okay, sir.
Okay, any questions? Finally, I'm asking. So, any questions? After this, I can close the meeting. No?
No, sir.
Okay, okay. Okay. So, bye.
Thank you, sir.
Thanks. Thanks, everyone. Bye.